Dear colleagues, we shall begin. It seems that it's high time to start. The microphone is on. And allow me to start our session. So, distinguished colleagues, and we are beginning the panel session for the defense of the thesis of Alexei Kononov. The thesis is submitted for the academic degree of the Doctor of Sciences in Physics and Mathematics. The specialization is 010407, Condensed Metaphysics. The topic is Electron-excited states of DNA and DNA complexes with silver nanoclusters in accordance with the order of St. Petersburg State University 3963/1. I, Alexei I, the professor of the Department of General Physics II, have been appointed the chairperson of this dissertation board, and the order approved the candidates for the of our board. And allow me to introduce them: Alexei Pavlotsky, Alexander Shikin, Konstantin Taraverov, and allow me to not to give all the titles: Alexander Gimansky and Svetlana Santer. Pleased to see you, Svetlana. Professor of Potsdam University. She's with us from Germany. So everyone is present, everyone hears us, and we also have our candidate for the degree, Alexei Kononov. And in order to improve the quality of our connection, kindly turn on your microphones when you speak, and otherwise you should turn them off, not to generate noise. And I would like also to inform that our panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted into English or into Russian if there is such a need. So as for our broadcast today, we have an email address given there, and all the listeners can voice their opinion or send their questions to our candidate for the degree on the dissertation and on the scientific discussion of his report. And our technical service will submit these questions to me, and I'll answer during the session. And these questions should be on the dissertation and on the scientific discussion. And please don't forget to introduce yourself and your position. The questions that have nothing to do with the scientific discussion will not be voiced. Under the order of the procedure of granting academic degrees at St. Petersburg State University, approved by normative acts, the session of our dissertation board is valid, providing 2/3 of the appointed board members are present. So no less than 4 people. So no less than 2/3 and no less than 4 people. So we meet these requirements. Our dissertation board consists of 6 people. Everyone is with us today, including one member who is with us remotely. And we have multimedia connection with everyone. Therefore, we have a quorum. And our session should not last more than 3 hours. And our today's agenda is as follows: the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements, chairman's reply to questions, if any, so 5 minutes for that. The candidate's short presentation providing an overview and findings of the research, no more than 20 minutes, but I believe won't hurry you up. Questions to the candidate regarding the presentation, no more than 2 minutes for each question. The replies to questions by candidate, the reports on the thesis, the board members will be taking the floor in turns to provide their reviews and questions. And the candidate will also deliver the reply. So that's 10 minutes for each speaker, for each reviewer. And also the external reviews, then chairman's report on the thesis. So 10 minutes, I believe. The candidate's comments about the reports on the thesis and replies to the questions, no more than 20 minutes. Then open discussion. If anyone present is willing to deliver a report or state their position or ask questions or provide offers on the topic of research, no more than 2 minutes each. And everyone willing to speak out, please don't forget to register in our form. And to introduce yourself before you speak out. Then, the chairman will ask the questions submitted during the broadcast via our website. And this will be broadcast once again. Then candidates' replies to the questions, no more than 2 minutes each. Then 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. And this discussion will not be broadcast, so that's 5 minutes. If we want, we can miss that. Then open balloting, vote counting, and recording of the results in the protocol. Then making a decision on whether to confer the academic degree or not. And finally, candidates' closing remarks, no more than 2 minutes. Distinguished colleagues, if there are any questions or objections on this agenda, please feel free to say. I believe there are no questions. So no objections, then let me begin. But before that, I kindly ask you to switch off your mobile phones. Thank you very much. Yeah, I offered to do that to you, but I didn't turn off my mobile phone as well. Okay. So, Chairman's short presentation. The thesis of Alexei Kononov for the academic degree of the Doctor of Sciences in Physics and Mathematics. Specializations 010407, Condensed Matter Physics, is titled Electron-excited States of DNA and DNA Complexes with Silver Nanoclusters. Thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University, issued April 30th, 2020, number 6810/1. Alexei Kononov has prepared his dissertation based at St. Petersburg State University. The list of 14 published works describe the main research findings, and they include no papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 13 papers in publications indexed in Web of Science and Scopus. The candidate has submitted the full set of documents to the Academic Secretary. The above-mentioned documents comply with item 12 of section 1 on the order of the procedure of granting academic degrees at St. Petersburg State University. All the documents submitted by the candidate comply with the requirements, and they are kept at the certification file, and the curator of the defense, member of the Department of the Dissertation Board, has all the copies. That's Madam Karpova. And before I give the floor to our candidate for the degree, dear members of the board, do you have any general questions to the applicant? And do we need to consider the entire list of documents submitted for the defense? So, no need for that. Yeah. No questions? Okay. Then short report by our candidate for the degree. Please, Alexei, you have the floor. Thank you. Good afternoon, dear colleagues. This thesis is actually a follow-up to the topic that I started my career many years ago. That's the DNA-based supramolecular structures, Photonics. That's an extension of my PhD thesis, and several years ago I managed to return to this topic. And this thesis is a result. And I also included the research of the recent years in it. So these are DNA structures and DNA complexes with silver nanoclusters. DNA is the most important molecule. That is, by the way, the title of a famous book by Frank Kamenetsky. Remains an object of interest to researchers in various sciences, attracting their attention with its unique properties. First of all, that's the ability to self-organization and conformational transformations. On the one hand, from the point of view of natural sciences, this interest is explained by a natural desire to understand how the real world works. That is the field of life sciences. And on the other hand, this interest is due to the desire to create different nanoconstructs, nanostructures based on it in nanoelectronics and nanophotonics and nanomedicine, using its unique characteristics. In this work, I focus on electron-excited states. These are the states that can be implemented as a result of absorption of photons. DNA. Light is absorbed by nuclear bases that are connected by sugar phosphate chain, and the DNA structure is mostly stabilized by stacking, by DNA stacked structures, and also by hydrogen steams. And from the point of view, yes, the interest to such states, electron-excited states, is explained by the fact that we all are influenced by solar light somehow or other, and the interaction with it can lead to different DNA lesions as a result of photon absorption. For example, you see these neighboring couples of pyrimidine, of cytosine, or thymidine bases that can lead to a rather dangerous photo project that's being formed in time less than 1 picosecond, and that is the so-called cyclobutan pyrimidine dimer that's being formed as a result of combination of cyclobutane ring and these two connections, C5, C6. This product is oncogenic, and it leads to skin cancer. The efficiency of interaction of DNA with solar radiation is determined by the degree of overlap of the spectra near the terrestrial surface. So this small area of overlap of two spectra is responsible for the entire photochemistry that takes place with DNA participation under the UV light impact. And it's clear that specific changes for its conformation can lead to changes in this overlap and efficiency of interaction. In a range of works, this spectrum of formation of photo products, including this cyclobutane butanes, they are different, and this hints at heterogeneity of the system. And the conformation heterogeneity of DNA is well explained because DNA can be found in three main forms of this double-stranded form, and there's a wide variety of some non-canonic forms that are quite rare, yet we still see them in cells. Conformation heterogeneity can certainly lead to spectral heterogeneity, so these are different forms that can absorb light in a different manner, and they have a different spectrum of absorption. Well, spectral heterogeneity was described in literature, in activity spectra, in luminescence spectra, in excitation spectra. And spectral heterogeneity was also mentioned in works on studying of the dynamics of electron-excited states. And one of the goals of my research was to study the impact of conformation on electron-excited states. What is this interaction between conformation and different characteristics of EES? And to this end, in this part of work, we resolved two main goals. So here you see them on the slide. And to resolve the first problem, we calculated the absorption spectra of nuclear bases stacking dimers in different conformations. As for stacking dimers, these are two neighboring nuclear bases in the DNA chain that are interacting between themselves in the stack. And as for conformation variety that we studied, we had conformations received in molecular dynamics of thymine oligonucleotide with 18 bases, and there was also a wide variety of structures that we've taken from PDB database that have quite a lot of conformations, including the nucleic acid conformations. And we used two basic conformation parameters for analysis. That's distance between the centers of the C5-C6 bonds and the torsion dihedral angle between them. In DNA-B form, these parameters make up 4.6 angstrom and 36 angles, and the angle of 36 degrees. And if we consider the interaction of bases, the spectrum changes the following way. So we can consider it in a thymine dimer. In thymine, the wavelength has one intensive EP transition, and with the interaction in interaction with the neighboring bases, this transition splits into two, and we have this split and shift of energy state against the maximum. And for DNA, for B form of DNA, that's rather small, and it makes up 0.1 electron volt. And it does not lead to serious changes in absorption spectra considering monomers. So we've analyzed different conformities, different conformations from the database and molecular dynamics, and we calculated the absorption spectra of dimers in these conformations, and we've also considered the dependence of a shift in energy state from these two parameters that I've mentioned before. For B form, the shift is 0.1 electron volt, as I've already mentioned, and that is the conformation sphere that is demonstrated by a blue rectangle on this slide. And with a drop in distance from 3.5 to 3 angstrom, a low energy state shifts to 0.3, 0.4 electron volt against the maximum, and you see it in red here on this map. So here are the examples of conformations in which we found such couples of bases with a shift. of a low energy state. Over here, two examples. To the left, these are confirmations of molecular dynamics data, and to the right you see the confirmations of non-canonical structures in PDB base. And the dimers in these structures, in which we see strong shift of energy state, they are united by, you see they are circled by in red, and the majority of such dimers were found in structures that demonstrate the distortion of chains, bending of chains in interaction sites with different ligands. And as for quantity, this measure of interaction of solar radiation with these structures can be assessed using spectral efficiency. Spectral efficiency is the should be calculated like that. You see the description on the slide. And if we compare the two spectra for B form and for distorted dimer with a significant shift in low energy state, we see that these two integrals are strongly different by several orders. Thus, we can make a conclusion that possibly these structures with strong shift in energy state are more prone to the impact of solar radiation at the surface of Earth. And thus, the first finding of my thesis was as follows. The presence of DNA structures with low-lying EES is confirmed by the calculation of base-stacking dimers excitation spectra. Nuclear base-stacking structures with geometry determined by the distance between the centers of the C5-C6 bonds in a range less than 3.3 angstrom and with a dihedral angle less than 50 degrees exhibit low-lying EAS of excitation of exciton origin in the region of 300 nanometers of the nucleic acid excitation spectrum, and these structures are the most effective hotspots interacting with terrestrial solar radiation. And one of non-canonical DNA forms that I've mentioned is the so-called Imotive structure. It emerges as a result of interaction between proton cytosine chains. So here we see the formation of non-canonic CC ties between bases, and two double helices intercalate, creating the so-called I-tetraplex or I-motive. And this structure was well known long ago, but only last year it was detected in live cells. And thus it was it has confirmed its biological importance. And these structures are of interest because its absorption spectrum, here you see it in the left on the slide. So it has a strong tail, long wave tail. And the origin of this tail in literature was not discussed practically. And in this work, we studied the change in characteristics of electron-excited states in transition from one helix chain of cytosines to the Imotive structure. And we also tried to understand the origin of this long wave tail. So experimentally, we studied the spectral properties of conformations formed by cytosine chains 10 bases long that are in the hairpin form, and they're intercalated, forming this Imotive structure. So you see it, this scheme here on the left. And theoretically, we calculated the spectra of excitation of the tetramer as a fragment of structure of Imotive from the database. We calculated the spectrum, and it was discovered that long wave state, energy state, shifts against the maximum of Imotive spectrum and against the maximums of monomers, neutral and protonated. And this shift makes up 0.3 electron volt, which, by the way, can be used to explain the origin of long wave tail in absorption spectrum of Imotive. And the analysis of densities of states showed that the majority of them are the states of delocalized excitation, so-called exciton states. And experimentally, as I've already mentioned, in absorption spectrum of such a structure, we observe long wave arm that shifts against the maximum to this order of 0.3 electron volts as in our calculation spectra. And also the presence of such transitions, electron transitions in this sphere, is supported by the curve of dependence of anisotropy from excitation, anisotropy luminescence over here. And luminescence spectra of Imotive have a long wave band, well pronounced compared with a single helix form and monomer form. And the differences were detected in kinetics of luminescence of these structures. For Imotive, in the luminescence kinetics, we observe significant contribution of long-lived components, and we see the change in anisotropy. And the component spectra were analyzed, and it turned out that long-lived components shift against other monomer components to the very same value of 0.3 electron volt as in low energy transition of absorption spectra. And above all, the formation of such components at a quick time scale happens quite quickly, because in the kinetics we didn't find any growing components, and based upon the well-known time-resolving capacity of the installation, we can conclude that the formation of these components happens quicker than 10 femtosecond of this capacity of our installation. And the combination of these facts allowed us to draw such a scheme of processes that happen in Imotive. So shortly after the absorption of photons, we see the formation of either a monomer-like state with localized excitation, luminescence at the band of 320, or delocalized state that preserves, and we just observe relaxation, and luminescence of such delocalized state is in the range of 370 nanometers. And later on, this delocalized state is likely to form axiomeres that are observed in other spectral experiments on a long time scale, a long wave time scale. And there are hundreds of picoseconds values. Thus, we shift to finding 2 of my thesis. In the Imotive form, the DNA absorption spectrum is significantly transferred to the red zone due to exciton-base interaction, and exciton state is relatively long-lived with a lifetime of several picoseconds. And it should be mentioned that in publications on the dynamics of excited states, this question about what is this term of delocalized state, what is this time of delocalized state, it has long been discussed, and there are no clear conclusions. And the question remains, and the result of this thesis gives us base to say that in a number of DNA structures at room temperature, such states are possible. And then I proceed to other part of my dissertation. These are DNA complexes with silver cluster. Complexes of DNA with silver and with other metal ions have long been studied from the point of view of biology to this structure. Because silver is well known for its antibacterial characteristics, and above all, silver complexes are of interest from the point of view of opportunity to use these complexes in order to create different nanostructures based on DNA. And an example of such structure is demonstrated over here. That's crystal structure of DNA with silver ions that was that we have observed in 2017, and it is a chain of silver ions stabilized by 2 DNA strands, and it is positioned as a potential molecular conductor. And another example of silver structures with DNA is demonstrated here on the left. That's also a crystal structure of luminescent complexes of silver clusters with DNA. So it's luminescent in this green area, and such complexes are considered prospective for future use in different bioimaging applications because they are luminescent. And shortly, a metal cluster is an agglomerate of several dozens of atoms And the main difference from large formations of nanoparticles is the presence of large electron gap, the gap between filled and occupied orbitals. And this makes luminescence possible, and based on them, we can create different luminophores in a broad range of spectrum. And in solution, they need stabilization by external ligands, and one of such ligands is DNA. And the synthesis of clusters on DNA happens in two stages. First of all, silver complexes are formed, and after that we add a reducing agent, for example boron hydride, and part of atoms form agglomerates of different form, and part can be luminescent. And initially it should be mentioned that the goal of using this complexes was to study the energy migration process in DNA, because these complexes can be strong acceptors of excitation energy. And as when I started this research, little was known about the complex structures and about photoprocesses in them. So the goal was of this part of work were aimed at determination of structure, then determining the radius and migration mechanisms in DNA complexes, and the study of basic photoprocesses in complexes. The first goal was to define the structure of these complexes, and it was resolved by a comprehensive experimental approach. And the goal was as follows. At the initial stage, we determined the structure of the DNA complex with ions, so the precursor formation of the cluster. This structure was defined using different experimental methods. We used circular dichroism spectra, photoelectronic spectra, mass spectrometry. And an example of such structure can be seen here. That's silver complexes with 15-dimensional polyoligonucleotide that form this dimer due to the CC connections between the neighboring cytosines in the chain, mediated by silver ions, the so-called AA silver-mediated bonds. And on the second stage, we needed to define this connection plot of reduced silver clusters, and oligonucleotide chain was modified, and the bases were replaced one by one by adenines, and we found it empirically whether they form luminescent complexes, and if luminescence disappeared, it demonstrated that in this spot of initial structure we had this silver cluster connection with DNA structure, and two neighboring cytosine couples form the place. They form this connection with the cluster. And the finalizing stage of finding this structure included theoretical QMMM optimization of complexes, that is, the bases and atoms of silver were described, and sugar phosphate frame and water environment were described with power fields of mechanics. And such an optimization finally led us to different structures depending on the number of atoms in the cluster and depending on the charge of the cluster. For all these structures, as we calculated excitation spectra were juxtaposed with experimental luminescence spectra, and as a result, those structures that demonstrated close coordination with experimental spectra were selected at the last stage. And we found several of such complexes. One of them can be seen here to the right. That's the complex that is luminescent in green. And here you see two clusters that are luminescent in green and in red. And the comparison of experimental and calculation spectra. And not only absorption spectra, we also calculated anisotropy and luminescence spectra, and also juxtaposed them with experimental data. As a result, we found several of such structures of luminescence cluster complexes that are luminescent in different spectral ranges. They all had specific characteristic that they shared, and they formed so-called protracted chain from silver atoms, for example, like here or over here. And thus, I phrased third finding that DNA-stabilized luminescent silver clusters have an extended shape realized in a cluster complex with a duplex or hairpin. Duplex and hairpins are needed to stabilize this so-called thread-like, filament-like structure of the cluster. The thing is that absorption spectrum of such structures in all DNA clusters, the absorption spectra and all silver clusters that are stabilized by DNA and luminescent clusters, they have such a characteristic like strong pronounced band of the visible light, and they lack bands up until ultraviolet range. And this spectral form can be performed only in silver atom chains. Yet, for this chain to be stable, it requires a stabilization by neighboring DNA strands. Well then, after the structure of the complexes was established, we studied the migration of energy, or rather energy transfer, along the chain of DNA with cluster complex. And the efficiency of such migration was defined as a result as a relation of intensity of long-wave band and ultraviolet band in excitation spectra of luminescence of our clusters, because long-wave band is needed for absorption and ultraviolet band is explained by DNA absorption. So the impact of DNA was determined exactly in comparison with the absorption spectrum of the complex. And for the three complexes that we studied, the efficiency was determined as follows. For stabilized cluster 12-dimensional hairpin, the transfer was from 12 bases, 15-dimensional duplex 21 bases, and for a stabilized cluster of thymus DNA it was 28 bases. The transfer rate was estimated directly in experiments on kinetics of luminescence of the complexes. We determined the growth time of luminescence in attenuation curve after excitation by ultraviolet pulse. 266 nanometers. There was the excitation of DNA, and we registered the luminescence of the complex. And as in these curves, these attenuation curves, we had no growth component, and this growth is due to the width of excitation complex that's demonstrated here, and this model takes into account the deconvolution with the complex. And as time-resolving capacity of such installations make up 100 femtoseconds, that is, the component that with a quicker time is something that you can't detect. Therefore, it can be said that the formation of such luminescence of cluster is formed in a time that is smaller than 150 femtoseconds, and this transfer from DNA to cluster happen in time less than 100 femtoseconds. And for thymus DNA case, to the right, we see the scheme of the complex structure and the transfer process for energy. As I've already mentioned, the energy transfer happens from 28 bases, and this structure had 14 bases in all in both strands, or you see 7 on each side. And this plot is rather prolonged, 7 bases on each side, and the observed speed, a rate of 100 femtoseconds, is not comparable with trivial Forster transfer mechanism. And another alternative is delocalization of excitation, at least at this plot of 7 bases, with a quick shift of, with quick transfer of excitation to this cluster and its luminescence. And based upon these experiments, we've made the wording for our fourth finding, that for DNA complexes with silver clusters, we can have efficient transfer of electronic excitation in regions containing about 30 nuclear bases along the helix in time less than 100 femtoseconds, and the transfer mechanism involves delocalization of electronic excitation in a region of about 5 nuclear bases in a single DNA helix. And it should be mentioned that from the point of view of DNA photophysics, that is the result that is also of interest, because the opportunity to form coherent oxytons of DNA and the localization of excitation have long been discussed and disputed in literature. So next part of my work was dedicated to the dynamics of excitation in silver clusters. And it should be mentioned that initially the methodology that I've already mentioned was to determine the efficiency of energy migration in complexes of DNA with silver clusters. And it required the knowledge of absorption coefficients for clusters, but as we didn't know them, we had to define them experimentally. And to this end, we used the method of fluorescence saturation spectroscopy, and it allowed us to determine other constants as well. The model is the most simple one that we considered in these systems. It was a three-tier model, and excitation dynamics of this sphere is described by a simple system of differential equations. We modified the experiment so that we registered the dependency of luminescence intensity from excitation energy of the pulse. The pulse was differed in length. We had 3 excitation regime: picosecond, nanosecond, and the so-called continuous excitation regime. And for these 3 cases, we used either the equations that could be received with analytical methodology in 2 cases, indeed in picosecond pulses and in continuous wave pulses. This system can be resolved analytically, and it allows us to make conclusions, but unfortunately here in the presentation I have no equations describing these dependencies. Yet shortly, the picosecond regime allows us to define absorption cross-section, this constant. Nanosecond regime of excitation allows us to define the formation of the so-called long-wave states. And continuous or continuum wave regime allows us to determine the deactivation constant of these dark states. And dark states are the states that are not luminescent. And such states in physics of molecules, these are triplet states. But in this case, in these complexes, I believe we have the state of charge transfer. And as a result, for 2 clusters that are luminescent in yellow, we found an exceptional rate of dark state formation 10 in -8 degree, taken to the degree of -8, and this leads us to the assessment of the efficiency formation of 20%. So 20% of absorbed quanta lead us to the formation of these dark states. And for the figures that we know for other clusters, the dark state formation efficiency was roughly 1 or several percent, 1 or 2. And compared to that, clusters that we studied demonstrated an exceptionally high percentage of dark matter formation. And as a result, we awarded fifth finding that complexes of silver clusters with DNA can have a high quantum yield of a long-lived dark state. And finally, in the final part of my work, I studied the shift dynamics of luminescence spectrum in silver DNA complexes clusters. So the dynamic Stokes shift. The general scheme of Stokes shift formation is here on this slide, and the origin of this shift, the nature of it, between the maximums of absorption spectra and luminescence spectra, is that these are two potential energy surfaces of excited state, and in excited state we see relaxation. This relaxation leads us to the fact that energy of vertical transitions is different, and this finally leads to Stokes shift, and the contribution to Stokes shift and relaxation can be done by several components. First of all, vibronic relaxation, the change in molecules, and environment relaxation. A solvent, for example, relaxation, or polymer matrix relaxation that stabilizes the cluster. And here on the right, you see stationary spectra of luminescence absorption, the cluster that works for 420 nanometers. And here we observe a rather significant Stokes shift of luminescence, nearly 4,000 reverse centimeters, and that's a rather large value, and this demonstrates restructuring, significant restructuring of the conformation of the complex in excited state. We registered the kinetics of luminescence and different wavelengths, and the result of these attenuation curves, the results gave us the temporal spectra. So you see them to the left, and to the right they're compared with stable luminescence in red. Here you see the spectrum that we got, and you see the amplitudes of exponents after deconvolution with excitation impulse. So practically that is the spectrum at a 0 time point. And as time resolving capacity of the installation is 150 femtoseconds, we can conclude that This luminescence, this shift in luminescence spectrum happens at a time of 100 or quicker than 150 femtoseconds. So in time less than 100 femtoseconds, we see the relaxation of cluster in excited state. And this result can demonstrate that the basic contribution to this relaxation is done by silver core of the cluster, this change in bonds between silver atoms and the change in silver and DNA clusters. And further relaxation is insignificant, yet we see it in the comparison of a spectra in picosecond and in a nanosecond scale. That's the relaxation of the solvent and matrix DNA, but it's insignificant compared to this swift relaxation of the complex core. Thus, we worded our final sixth finding. The Stokes shift of cluster luminescence is mainly determined by the rearrangement of cluster structure in excited state in time less than 100 femtoseconds. And in conclusion, I would like to give you the list of all the findings, all the provisions. So you see them on the slide. And also the list of published works, where you can find the main results of the thesis. That's it. Thank you very much. And I hope that I didn't take too much time. Too much. Okay, I beg your pardon for that. Thank you very much. This short report turned out not to be quite short. And questions to our candidate for the degree, do we have any? Well, I would ask one technical question. So we see this slide 18. Can you get back to that? And it has this split of absorption spectra into components. Well, one of the examples, 16 or 18, yeah. So the split into components. This one, yeah. This spectral form is rather smooth, you see. And where is this guarantee that this split is done correctly? And these shifts really are really this 0.1 electron volt or 0.3 electron volt. What are the criteria? Thank you for the question. I can tell about that in detail, about the spectra that we got. Well, 2 minutes. 2 minutes to answer. Well, the calculation spectrum is this calculated spectrum that gives us the energy of excited states. That's what was calculated. Then, the form of this spectrum, mostly these are fluctuation structures. Expansion of this spectra takes place due to fluctuation form. And the form of this spectra was chosen for each transition, and it was just the same as it actually is in monomer with one transition. If, for example, we have 2 transitions, we made convolution with this spectrum, and as a result, the resulting spectra were different. Oh, thank you. I got the answer. Yes, I see. Yeah, I understood. You've taken the calculation energy. So yes, that is the question. Any other questions? No, I believe the report was so detailed that there are no questions. Thank you very much. I have a question on slide 43. And this one. You demonstrate the study of positively charged silver cluster. It would be interesting to learn about the changes to be expected for neutral cluster. Why did you choose a positively charged cluster? And do you, for example, see negatively charged clusters? Neutral, yes, I know about the neutral ones, but as for the negatively charged, could you please answer? Thank you very much for the question. A really complicated question, indeed, because I show several of other slides just to illustrate the differences, the possible differences. The thing is that, just moving forward, as I'm going to answer rather close questions by Alexander Vadimovich in his review. Well, this question was partially covered. Well, I'll talk about it right now as well. Before choosing the final cluster structure, we carried out extensive work on studying the model systems, more simple and smaller systems. In particular, on this slide, for example, I'll show you so here you see the comparison of two cluster spectra, 4 atomic clusters with different cluster charge. As a result, when we see a change in charge from neutral to charged, we see this significant change. And that's the first thing. And naturally, when choosing more charged structure, we compared different cluster charges, and for each we calculated the spectrum, the excitation spectrum. And about the fact that their calculation spectra are strongly different, it gave us the basis to not to use certain structures, because they did not comply with our experiment requirements. And yet another point that should be taken into account, that was taken into account, that's the stability of such structures. And I'll show you one table to illustrate. This table is not included, was not published in the articles on the thesis, but it's one of our articles that illustrates the bonds energies of neutral or charged clusters with cytosine. And for neutral clusters, these energies and bonds are significantly lower. You see in the right column, these are the bond energies. So these are the calculation figures. For neutral clusters, these values are significantly lower than for the charged ones. And this is one of the reasons why we chose charged clusters in our experiment. But sure enough, if it turned out that the excitation spectra of neutral clusters would correspond the needs of our experiment better, certainly we would have made a conclusion to choose neutral clusters. But as our experiment required charged clusters, therefore we chose the charged ones, and this really shows us the bonds energies, neutral and charged ones. I believe you've already answered. Yes. Yes, thank you very much. It's clear that you've prepared quite well for that. Well, thank you very much. Other questions, if any? None? I believe everyone is satisfied. Then we shift to the speeches of our board members with assessments of their dissertation, and also the candidate can reply, and also external reviews. I believe we can answer at once, because otherwise it will be rather hard to remember everything. So please, Alexander. So don't read out everything, but the most important ones. Thank you very much. I'm really lucky to be the first one, and I have the words that were not mentioned before. Well, indeed, the work carried out by Alexei Igorevich, it's quite fundamental, but it is of significant value, because everyone who was working with photoactive molecular systems always thought about one specific problem: whether these systems would be stable, if we want them to be. And certainly the mechanisms of photodegradation, the reasons why they emerge in DNA molecules and in systems that they form, up until now, they remained one of the most relevant goals. And sure enough, we should mention that this work is very relevant, exceptionally relevant, and has a lot of opportunities for practical application. I won't list all the peculiarities of all the chapters. Overall, the work created a very comprehensive impression of a very comprehensive work, finished work. And when I read the thesis, I had several questions. First question was already was just like the one that was already asked on the presentation, that you state that the calculation data in the chromophore core of the complex has a charge of +1, +2, and we've seen the catastrophic changes in the maximum provisions, in the maximum positions that they cause. And the question was, what will be with the neutral clusters? So we've actually received a detailed answer to that. Then, femtosecond pulse rate length is 350 femtoseconds, and we see it in light scattering in water. And the question arises, how do we make a conclusion that there is less than 100 femtoseconds of excitation time of researched molecules? And the last thing is that you've studied the reasons and changes in spectra of molecules and in molecule systems with clusters. But the question was about whether you studied photostability. And indeed, yes, as far as I see it, in this work that was published, it has this information about the photostability of molecules. Well, not that exactly. Maybe I'll start with the last question. As for photostability, I did not study it particularly. There were a range of literature data, in a range of publications. Silver clusters stabilized by DNA were positioned as photostable compared with other luminophores based on dye wear. And that is one of their considered advantages if we replace traditional dye wear on clusters with clusters. And they all have different behavior, and our experimental assessments demonstrate that some are stable and some are very quickly disintegrating. Yet such a photostability, it was tracked in experiments with lasers, time-resolving experiments using spectroscopy of saturation. When experiments were lengthening, and there was a large dose of radiation that was absorbed by the clusters. We studied their stability in luminescence and on absorption. And we've tracked this destruction of structures so that it would not exceed 10%, because this would have an impact on the analysis of data. And that's about photostability. Yes, as for the previous question, you've already answered that. Yes, the previous one was about time-resolving capacity of the installation. You see this assessment of 100 femtoseconds. It's used in installations, and it's based upon the fact that the error of defining this width of excitation band, it makes up plus or minus 50 femtoseconds, and as a result of the convolution, this exponents which are smaller than 100 femtoseconds, they are not quite reliable. And you can ignore them in experimental curve modeling. Therefore, everything less than 100 femtoseconds, it can't be tracked on these installations. Thank you very much, but overall the work makes a very good impression, and as far as I see it, Alexei deserves the degree of the Doctor of Sciences in Physics and Mathematics, and I urge the colleagues to support this decision. Thank you very much. Alexander Mikhailovich, please. Well, I'll be short, quite short. I won't dwell upon the measurements, the studies, but I would like to mention that a very extensive finished cycle of work was carried out, and this research is of a very high scientific and technical level. The credibility of results is not questioned, and as for this work, I have no objections, and I fully agree with the fact that Alexei should be granted the title of the academic degree of the Doctor of Sciences. Yes, we have nothing to reply here. And now let's listen to Konstantin Konstantinovich. Well, allow me not to voice entire review. Well, first of all, introduction. The author substantiates the relevance of the problems and formulates the goals to be met, and also formulates scientific novelty of a range of proposals, and also the practical relevance and the findings that for the defense that he dwelled upon during his presentation. Second point, as for relevance, I'll mention it later. Second point is that I would like to dwell upon the methodological chapter, the second chapter. I believe that is a particular characteristic of this work, that it has a combination of experimental and theoretical methods. And in methodology, the author gives his introduces his novelties, the method of nonlinear spectroscopy and saturation, luminescence. So in this form that the author offered, I believe they were quite interesting and useful. Then we can have two fields, consider two fields. Chapter 3 and Chapter 4 consider this low energy excited states, and in chapters 5 and 6 we see the issue on silver clusters that in interaction with DNA, and everything is described quite well. And basically each of these fields would, I believe, would make up a good doctoral thesis, because you received very valuable results. And as for silver nanoclusters, Alexei's work and his group work, they are well known internationally, and they are published in very good journals with a high impact factor, and I believe that's pretty good. Now I have a comment, certain comments, certain remarks. This first slide, as far as I believe that you've given, to my mind, it's a kind of a comparison of absorption spectrum and solar radiation spectrum. This overlap is quite insignificant, but using low energy levels, it seems to grow. And the question arises that indeed solar radiation can have this negative impact, harmful biological effect. I do not fully agree with that, because basically biological tissues are transparent only in 650, 850 nanometers, so that is the spectral transparency level of biological tissue. And strictly speaking, DNA is well protected from solar radiation. Yet we can talk about solar radiation impact on skin. So this is of interest to medical sphere. I believe you should take that into account, and I believe that you've taken that, you've considered that in your report. And at the same time, though I questioned this wording of relevance, I still would like to say that all the issues considered in the thesis are particularly relevant, though I believe I have certain thoughts that some of the results that you received, they defined a new approach to the DNA structure studies, because there's a lot of interaction in the canonic structure of nuclear nuclear bases interaction, and you consider the interaction across the chain. And that is of particular importance, especially due to the fact that DNA is considered as quite a promising material in a number of nanostructures. And I won't dwell upon because everything was well described in publications. So that, I believe, is a relevant aspect. And I have some short remarks. The work is very well written, though I mentioned certain problems, insignificant ones, but I didn't write about it. And some electron-excited states, you give them with this abbreviation of EES, and it's not that good that you don't have abbreviations list, but that's a small remark, insignificant one. And you also give a slide with absorption spectra of DNA bases, and it seems to me that in this dissertation it would be wonderful to discuss them as well, because there are things to be discussed here. That's it. Overall, the work is really pretty good. I won't go into details, but I want to say that sure enough, Alexei deserves the academic degree of the Doctor of Sciences. I beg your pardon, I'm just used about talking about biological sciences. So I urge all the colleagues to vote for the conferring of academic degree. Thank you very much, Konstantin. I believe there's nothing to answer. Well, I would, but I believe distinguished Konstantinovich does not insist on that. Therefore, I won't give a detailed answer. Though I have an answer because the question is quite good. And I believe, yes, short answers, yes. As for the last remark, or the last question, I agree with it, that monomers should have been paid more attention. But the thing is that monomer excited states, even in monomers, they are not that universally accepted and described in literature. And up until now, the experiments and discussions and calculations go on about how many of them there are and what is their contribution to photochemistry. That's a specific topic. And in my thesis, I tried not to consider that in order to reduce the number of pages. And as for interaction with tissues, interaction of solar radiation with tissues, here Konstantin is right, sure enough, that the tissues are rather well protected from this harmful influence, yet skin in this regard still remain protected, and it gives the major contribution to these cancerogenic effects under the solar impact. And studying the activity spectra that were mentioned in the question, certainly that's dealing with the issue of skin as well. And one of the examples of such works is given here, that the formation of cyclobutane dimers after radiation of skin. Thank you very much. So please don't talk about cancer any longer. I believe that's enough. Don't scare us. Well, too much solar energy is harmful. Yes, that's it. Okay, let's move forward. Alexander, you have the floor. well, I had a range of comments, but half of them are just editorial ones, and are mostly connected with the fact that I did not have a good understanding of Imotive and non-canonical forms, and this illustration was not quite clear. And if I didn't have the presentation, if I wouldn't get the presentation, it would be hard for me to understand. But I understood it thanks to the presentation. And as for the editorial comments, I believe I won't just pay time on that, spend time on that. One technical remark is the use of two parameters for the description of molecular orientation. I worked a lot with quantum mechanical calculations, and as far as I see it, how these dimers can be reactors, you should have 6 parameters to define or to determine the orientation of molecules against each other. Some others are you optimize other parameters, or where do you get them? I didn't see it in the methodological part. So you have a map on 2 parameters, and as for other parameters, are they optimized or what? Maybe you can answer at once. Is that all? No, could you please? Well, I can answer everything at once or one by one. Okay, others. Basically, as for the leftover questions, there are 2 of them. One was already mentioned. It wasn't quite clear for me. How did you choose the structures, nanocluster structures with different models of DNA? So there are such phrases like there is this wording, until we achieve reasonable agreement. So it was not quite clear what structures were analyzed and what is reasonable agreement here. And also the R factor analysis, I believe they have something in common, that some way you should have this percentages and split it of intensities, signals of X-ray range. And as far as I know, for the structure to be used, you need up until several reflexes per atom, so that this system would remain sure. And certainly you can choose a range of solutions that would suit this limited data selection. So that is the question of validity and lack of alternative. This was the first question of those important ones. And it was not quite clear for me why you have these dark matter states of clusters, how they emerge. Alexei mentioned that it's connected with the charge, but I've seen that these are triplet states, and I believe that it is connected, that dark state is connected with spin band. But as far as I know, heavy atoms, and there are quite a lot of them there in these clusters, they give very significant interaction that should abandon this, that should take away the band. And in luminophores, you have complexes of iridium, platinum, palladium, and other heavy metals, just for this triplet excitons to become luminescent. And that is why this phrase was not quite clear. That you have this radiation spectrum, and they can be they can be the demonstration of non-luminescent dark cluster. But Thing is that I did not quite understand why they shouldn't radiate. That's why I had these secondary questions. And basically that's it, what I got. And some not quite good style phrases, but I believe that these are quite negligible. Thank you very much for the questions. I'll try to be short with my answers. As for parameter choice, indeed, the number of unified parameters that define the configuration. Why did I take 2 parameters, and why there were those parameters? These 2 parameters reflect the proximity of bonds C5, C6 in the nuclear base couple. And these ties is something that we have in the formation of cyclobutane ring and dimers. That is why quantum chemistry of these dimers studied this question, and it is believed that specific parameters allow to create these dimers, and other parameters do not allow that. And there's a range of these parameters for the bond length of D and for torsion angle mu. And specific area is selected that from the point of view of theoretical chemistry allows this reaction to happen, and happen quite quickly. And experimentally it happens within 100 femtoseconds. So from the point of view of correspondence, well, the goal of this work that I've mentioned was to consider the conformations that can well absorb the solar light. But that's one thing. It could have turned out that the conformations that are potentially incapable to be influenced by photochemical reactions absorb solar light quite well, but from the point of view of photochemistry, they wouldn't be prone to this strong influence of solar radiation. That is why it was important to understand that these conformations do not go beyond the borders of the allowed range from the point of view of chemistry. Yes, I had an impression that you got some calculations. No, there were no additional calculations performed, and it was provided that other parameters are in a kind of range defined by stacking interaction and sugar phosphate frame. And it would be interesting to have an analysis of spectra from the point of view of other parameters, but that would require more structures, and the structures are quite limited for such an analysis. Yes, if you had always these stacking structures, I would understand it, but those were perpendicular, and we are not talking about stacking. Maybe that was a sugar phosphate frame that restricts it. Yes, there are such structures as well, but what's important is that all research structures in which the distance between the bonds was considered, it turned out that they had good absorption capability. Yes, I understood. Thank you. Yes, there were 7 remarks. If this was just the first one, no, just 4. Just 4 left. Yes. A few words about the unambiguity of cluster structures. Yes, as for dark matter states, I'll show the slide once again. One question was about this third state that's given here as the dark state. Indeed, as it's mentioned in my report, in ordinary molecules, these are triplets with dyes. But in this case, its nature is unknown, its origin is unknown, and literature has it that such states are the states with charge transfer from cluster to DNA or vice versa. And as for charge transfer states, they are not luminescent in organic structures. Unambiguousness of these clusters. Yes. Yet another question on non-luminescent components. That has a lifespan of 200 femtoseconds with luminescence. Well, the thing is that in a stationary luminescence, it's not observed, because quantum yield is proportional to the lifespan, and the lifespan is quite short, 200 femtoseconds, and in stationary spectrum you don't see it, but you can include that in the curve when you have time resolving experiments, and this spectrum was given here. That's about the dark states. And the last question was about the choice of structures. Yes, it's not well described in details in the thesis. Yes, I agree with this remark. This was done just to be short, but actually we've carried out really huge work that started with some small clusters, and in particular, if Alexander remembers, he reviewed the work of my master's student once that was dedicated to the study of structures and spectra for free clusters of various forms. This was the first selection stage of structure similarity that could be used in DNA complexes. The next stage was to study the cluster complexes of different forms, for example, these ones, dichotomic, with different bases, with different atoms of bases, and in particular you see this example over here. Three atomic clusters, one neutral and one with +1 charge, and multiple variants of bonds with cytosine, thymine, nitrogen, oxygen atoms, and you see that the state and the spectra are different quite frequently, and this gave us the preliminary choice of structures to be used. Further on, we studied different structures as for full atomic cluster, answering the question of Svetlana, I've already mentioned that we studied large complexes with DNA molecules. And partially I've already demonstrated these examples. And that's what I wanted to say here. Certainly, we do not claim these structures to be unambiguous. But the thing is that we didn't have crystals of such structures because they're very hard to get, to generate. And as a result, we offered the method that would allow to detect the most probable structures of these complexes in solvent, in solutions. And above the, not only we should mention this work on small or free complexes that I did not mention in my thesis, but it was also important to use experimental methods to define the plots of connection, these bond plots, and this would guarantee the successful final result, because we could foresee the structure, predict it, calculate, optimize it using this spectrum of optimized complex and compare it with the experimental one. And these calculations were performed by Ruslan Ramazanov, by the way, on the optimization of these complexes. Initially, he was a PhD student and then a postdoc of our department and a member of our team that worked on the grant. And that is really impressive work that was performed. And overall, optimization methodology for such systems was not described in literature, so you had to invent it, to write it down from scratch. And right now, well, Ruslan no longer works with us, but we continue these studies on the optimization, and it is carried out with different methods, and the results. Yeah, I see. You've already mentioned that it's hard to guarantee 100% validity here. Yes, compared with crystallographic structures, you can't you can't guarantee 100%. But the fact that you are being based on some notions and on some experiments, and you carry out your search in solutions, and you use optimization, I believe that's quite correct. And this just adds up the validity to the validity of these structures that you use. I agree with that. So, are you satisfied with the answer? Yes, quite satisfied. And I would like to support these positive assessments by my colleagues. And I believe that Alexei deserves the conferring of the academic degree of the Doctor of Sciences. Yes, okay, so we had a discussion on dark states. Yes or no, shortly, can we say that these dark states can demonstrate in this delayed luminescence? Yes or no? This happens sometimes when it has an impact on the lifespan. Well, in this case, they are luminescent. And you're... So you did not mean that? No. Delayed luminescence is a different thing here. Yes. Yes, I just thought it could be relevant. Thank you very much. Then our foreign representative, Svetlana Santer, from the University of Potsdam. Please, Svetlana, you have the floor. I'm not sure where to address. Yes, thank you very much. Distinguished colleagues, First of all, I would like to thank you for this chance to be the member of the dissertation board, and I'm quite honored to join you today, because for me this place is my alma mater. I'm also a graduate of this department. In 1996, I defended my master thesis on interaction of DNA with anti-cancer and platinum. And I'm really pleased to read the thesis of my colleague, Mr. Kononov, and it was very important for me in the assessment of this dissertation that it's being based on the results of 14 articles that were published in high-impact journals, like the Journal of American Chemical Society with an impact factor of 14.6, and Journal of Nucleic Acid Research with an impact factor of 11.5, and Scientific Reports with a very good impact factor of 4, and a Journal of Physics and Chemistry with a good impact factor. What does it mean, dear colleagues? It means that 30 other leading experts in chemistry and physics of soft and condensed matter had a very good assessment of this work, and they decided that these works deserve to be published in top journals. And as for the text of this dissertation, I would like to emphasize that I was pleased to read the introduction, as it was mentioned, where Alexei had a very detailed overview of DNA physics as a molecule and in complexes with clusters, and the introduction is very well written. The English is quite exceptional. I really enjoyed reading this introduction, and it is quite very good from the point of view of its didactics. That not only gives you the basics, but also new discoveries needed to understand the results. In my review, I commented the results in detail, and I've also emphasized the importance of delocalization description in 5 nucleotides of a DNA chain. Therefore, I would like to shift to questions. And in fact, I have just one, because I would like to hear the forecast. How do you think, how will your sphere develop in future? Because we discussed a lot of details, about a lot of simulations, but what's your vision of the future? What are the most important goals? What are the challenges? I'm not sure how to say it in Russian correctly. What are the problems? And what are your expectations? What are the developments that we're going to see in the field? Thank you. Thank you very much for all the kind words and for your question. It is really an interesting one. I did not get ready for this one, but I'll try to answer. Probably we're talking about further development of this topic. Indeed, it is connected with the fact that today laser technology is developing quite swiftly, and what's important is that we see more installations that allow us to study photo processes in ultraviolet range, where there is DNA absorption, or with time resolution of 10 femtoseconds. or dozens of femtoseconds. And it is particularly important because the majority of results that we know today, the results that I had in my thesis, they are limited to the time resolution of 100 femtoseconds. And what happens in a quicker time range, it still remains unknown. And analyzing the data that we got on installations with time resolution of 100 and more femtoseconds, it's obvious that there are a lot of processes that already finished by this time. And what happens at this initial stage, it is of particular interest in ordinary chemistry and photochemistry, and in DNA photochemistry, due to the quick development of this sphere, this research of components of DNA and structures and nanostructures based on DNA, they all would be particularly interesting. That's the first thing. The second thing, the second possible development line of DNA silver clusters is first of all to specify their structure, because I'm talking about crystal structures, because in the recent 2 years we've seen the publications. They are not quite numerous, rather rare, and you can calculate them with fingers of one hand. And they either described iron silver structures or silver cluster structures. And they give an understanding on the structure of these complexes. And they are quite in good conformity with the structures that are given in my thesis. This last finding saying that these luminescent complexes are protracted. And indeed, in crystallographic data, we see this film, but you see such structures, as far as I know, there are just 2 of them that were described in literature. I believe that is a possible development line here. And above all, the presence of more specific structures that were already defined, for example, using crystallographic analysis methods. It paves the way to elaborate on the methods of theoretical modeling of such structures and the calculation of spectra, because in this case you can take a method, optimize the structure, and compare it, contrast it with experimental data, and say whether this method is a good one, and if so, you can use it for different structures, for other structures later on. That's other way out, I believe. Yes, I believe that's quite a multifaceted topic. Yes, I can also add up to your vision, and I believe that the challenge here will be for Institute to buy such an installation for you to find this money, because I believe this should be done and they're quite costly. Thank you very much. And in conclusion, I would like to sum up that the thesis of Mr. Kononov deserves the conferring of the academic degree of Doctor of Sciences in Physics and Mathematics in Condensed Metaphysics. Thank you very much. And now it's my turn to sum up. Alexei, fortunately or unfortunately, everything was already mentioned. And I would like to join in to the opinion of my colleagues that the dissertation certainly deserves the academic degree of Doctor of Sciences in Physics and Mathematics, and I was really fascinated by the complexity of the object and by a range of methods. Therefore, I've just written in my review that the topic of this dissertation is really an exceptional achievement in the development of theory of studying of spectral methods of DNA research. And I would like to dwell upon just 3 points, 3 remarks that I've mentioned. On certain pages you have this impressive results demonstrating the change in spectra of luminescence in aging process, and I would like to find out to what extent these processes are, well, influence the data you received, because otherwise in comparison of data it turns out that after synthesis it becomes unclear what are the reasons of these differences, either in structure and construction or in aging changes. That's one point. Second point is the studying of influence of conformation on this excitation spectra, and author demonstrates that in the calculations performed they don't take into account the impact of environment, but in another part he says that this impact should be taken into account. Can you somehow assess it from the point of view of for example, error of these results? And third point is the stability of filament-like clusters. It can be stabilized in DNA itself. And as for free clusters, I was surprised by the fact that these are rather large, 4 or 5 atoms. They still remain flat. So where is this limit? Because at some point they should form a 3-dimensional structure, and you should minimize this superficial energy. Did you carry out such assessments or not? Thank you very much. I start with the last question, if you don't mind. And I show you the illustration at once. Indeed, the structures with minimal energy for silver clusters are quite typical until we have a 6-atomic cluster. And on this image, on this drawing, you see the data. That's not our work. That's an image from a publication, and it's not unique. It compares calculation spectra for optimized structures and experimental spectra received in low temperature matrices of inert gases in argon matrix. We observe good correspondence between them. Indeed, the structures are minimal in energy, they are flat, and the spectra has the same structures. And generally it shows, it indicates that experiments and theory go well together. But later on, for 6-atomic cluster, we see a mixture of structures in experimental spectra. We see the implementation of we see the differences in measurements, and for clusters larger than 6 atomics, they are all dimensional. For 6-atomic cluster, there is a small difference in energy between the flat cluster and the 3D one, and for clusters smaller than 6 atoms, they are flat. And didn't you take into account the clusters that are more than 6 atoms? No, we did not take them into account. Though, well, I don't give it in my thesis. No. No more than 6. Okay, that's clear. And as for 2 others? Well, as for 2 others, yes, about aging. That's not just aging. The destruction of one cluster and the formation of a new one in time. So how does this process happen? We did not study that in detail. And as for time changes of the spectrum, we observed them. The band of one cluster disappears, and we see the growth in the band or that characterizes other cluster in other spectral region. And in fact, we have this pumping out of bands. And we can conclude that probably one cluster destroys, deteriorates. And in these experiments, we were interested in initial and final result. And what clusters could be used in experiment, what is the time of their formation. And it was not very important for us. It was important that we could model their structure further on. Thank you very much. I'm quite satisfied, and I believe that this answer lays down the prospects of further development. Yes, and I believe it was, we had the question on the impact. Well, that's not a serious answer that I expect, because you see that there is such an influence, and it's clear that it's not quite significant. So yes, shortly, the thing is that this impact is well known from literature, because we're not the first ones to calculate the spectra of components of nucleic acids, so we're talking about that here. This impact is not quite significant, and what was important from the publications, we know that as for this value of exciton split that was important in our assessments, we don't have an impact here. Yes, thank you very much. It was already mentioned, it was voiced. Yes, and once again, there's a range of data here. And in the thesis, I don't give the impact of environment, because I have it in another part of my thesis, where I gave the final spectra of Imotive tetramer, because it was calculated in a water environment, and we've just tried to detect the impact of environment. Thank you very much. I'm quite satisfied. Is everyone satisfied? Dear colleagues, no questions whatsoever. That's why we can proceed. If there are any, do we have any questions that were submitted from other participants, not the members of our board? So please. Yes, do you hear me? Good afternoon. Vladimir Bakolev, senior researcher of the same department of molecular biophysics and polymer physics. Why I want to speak out, because of everyone present. I've known Alexei for a very long time. We were fellow students, and we worked in a group with one advisor. Then we worked in a group that I headed, and then Alexei started working in a group that he had with a lot of young, promising scientists. And as for the thesis, I would like to mention that the study of electron-excited states of DNA and its components, it is the imotive of Alexei's scientific activity from the very start, from the time when we were students. Once we studied the components of nucleic acids, and his PhD thesis was dedicated to the issue as well. And here I would like to mention that all the works given in doctoral thesis, they were published in the most recent 4 or 5 years, though you could give quite good works of 90s or 2000s in the photochemistry and photobiology journal, for example. But he still managed to do without it. And I just want to mention how efficiently he managed to work with during these years, because he has a team of experts and he executes a range of large grants, and this is done. This was done during several years. So I'm really glad for him that he have grown so much, and I'm really proud that I worked with him. So, very good result. So please, Vladimir, register in the form. If anyone else is willing to speak out, okay. No external reviews, or questions, or comments. Okay. And if so, the question to the members of the thesis board: do we have to stop the broadcast in order to discuss, to have a secret ballot? No, everyone spoke out openly. That is why we won't have this break. Okay, if we don't need a break, let's continue. So we continue the broadcast. And we can check whether we see and hear each other. So that's the question to you, Svetlana. Svetlana, as far as I see, you hear as well, and everything is okay? Okay. So let's raise the question on granting the academic degree of Doctor of Sciences in Physics and Mathematics. So please, everyone, I ask everyone to speak out. Alexei? Yes, I already spoke for that. And my opinion is unchanged, and I believe that Alexei deserves the academic degree of Doctor of Physics and Mathematics. Alexander? Yes, I would like to repeat that a lot of work, a finished cycle of research was carried out, and I believe, I support this idea, that Alexei deserves the academic degree of the Doctor of Physics and Mathematics. Yes, Konstantin Konstantinovich, yes, I support the opinion of my colleagues, sure enough. Alexei deserves the academic degree of the Doctor of Sciences in Physics and Mathematics, and I support it. Thank you very much, Alexander Vladimirovich. Yes, I do agree. Alexei deserves this academic degree, and I have no doubts about that. So I address this question to Svetlana. Yes, I would like to join in, and I support my colleagues that Alexei really deserves the academic degree of the Doctor of Sciences in Mathematics and Physics. Thank you very much. Now that's my turn to speak, and I really support the opinion of everyone else that indeed Mr. Kononov deserves the academic degree of the Doctor of Sciences, and I believe that's not quite hard to calculate all the votes. 6 members of the board voted for the granting of academic degree, and Natalia, I believe you can write it down that everyone supported the granting of academic degree, no one spoke against, and no one abstained from the vote. So the decision of conferring of the academic degree of the Doctor of Sciences in Physics and Mathematics in a specialization 010407 Physics of Condensed Matter is taken. And dear colleagues, as our session was broadcast and organized remotely, do the members of the dissertation board or candidate or our candidate for the degree, do you have any comments on the procedure? No comments? Okay. Now let's give the floor to our candidate for the degree, Mr. Kononov, for the finalizing remarks. Thank you. Well, as I've already mentioned, my thesis was based upon numerous works published in recent years. And a lot of people participated in them, and these are the co-authors of my publications given here, so all of them listed here. First of all, these are my students, my PhD students. Second, these are the employees of our department, the employees of our university, of other universities of Russia, of institutes that are not only Russian. And that's quite a large team of co-authors. And without them, this work would just be impossible. And I'm really grateful to all of them for the participation in these projects, in these works. Then, as Alexander Bakolev shortly mentioned, I would repeat that without mentioning of these people with whom I started working, it would be just impossible not to mention them, because I started my research activity with Mr. Rapoport, and there were Alexander Bakolev, Vera Belikova there, Anatoly Valevsky. So this was our team. The team that I started working with on this topic. Then, unfortunately, there was a serious break due to different reasons, and I worked on different topics. But over the recent years, I managed to get back to the topic, and I should mention yet another person. And I'm grateful to him. That's Vera Adamchuk. Unfortunately, she left us, and due to her moral and organizational support, I managed to perform the majority of these experiments. And indeed, I would like to thank all the members of the dissertation board that agreed to consider to review my presentation, to review my thesis, because otherwise it won't happen. Thank you very much, everyone. And I'm grateful to the technical group that provided the technical support. I would like to thank Natalia Karpova. And thank you very much to everyone who was present remotely or here with us. Thank you very much, everyone. Well then, thank you very much. Alexei, I believe we can congratulate you with a successful defense. So everything was wonderful. And I believe here we can close our session, and I believe we can turn off our broadcast.